Watch this runner. To capture them clearly as they barrel toward us, a camera has to physically shift heavy layers of glass to bend the light, aligning everything perfectly before the runner takes another step. Older autofocus systems relied on something called contrast detection. The camera didn't know where the runner was in space. It just knew that sharp edges have high contrast, so it would drive the lens forward and backward, checking the image over and over to see if it looked sharper. This chart shows how that lens position changes over time. Notice the erratic wave. The system has to guess, push past the point of maximum sharpness, realize it went too far, and then reverse direction, a stuttering effect known as focus hunting. That trial and error process eats up critical fractions of a second. By the time the internal motor finally dials in the right alignment, our runner has already covered another 2 meters, leaving us with a blurry image. Catching high-speed action requires a system that eliminates the guessing phase. We need a way to mathematically calculate the necessary lens position on the very first try. Let's stop the clock right here. To see how modern cameras solve this, we must look past the lens to the image sensor's microscopic surface. Most modern cameras use phase detection autofocus, embedding thousands of specialized pixels directly into the sensor that act like 2 tiny eyes, looking out at the same subject from slightly different angles. In this sensor diagram, specialized pixels intercept and split incoming light into 2 separate streams. When in focus, these streams converge perfectly on the focal plane. Because our runner is moving, the streams fall out of alignment, leaving a measurable gap. This physical misalignment provides the exact data points required to bring the subject back into focus. Look at this bracket spanning the overlapping shapes. The processor instantly measures the exact physical distance of that separation. That measurement provides mathematical coordinates for focus correction, telling the camera exactly how far the lens must move and in which direction. While contrast detection asks if an image is sharp yet, phase detection asks, how far out of focus am I and which way should I move? Armed with those coordinates, the internal motors take over. They drive the lens directly to the target position in one fluid motion. This movement is efficient. There is no oscillation or backward correction, as the system doesn't need to hunt for sharpness. The camera resolves the focus problem mathematically before engaging any physical gears, reducing a process that used to require several lens adjustments down to a single direct movement. When we let the clock run, the result is immediate. The runner completes their stride, captured with sharp detail at the precise moment. The camera performs this complex geometry thousands of times every second to maintain a continuous lock on the moving target. In modern systems, this mechanical speed is combined with artificial intelligence to improve subject recognition. Because phase detection handles the mechanics of focus instantly, the main processor has the bandwidth to identify specific targets. In this high-speed scene, you can see tracking boxes locking onto eyes, faces, and vehicles. This provides video creators with smooth focus transitions and reliable tracking, holding on to a moving subject even if they turn away or are temporarily obstructed by something in the foreground. Phase Detection Autofocus provides the data that makes these tracking systems possible. By measuring light through geometry, it gives photographers the precision needed to capture high-speed subjects with repeatable accuracy.